Okay, welcome to our second video on DC motors. So let's put together some of the ideas that we came across in a previous lesson, and just to quickly remind you, you remember that the two ideas we need to be aware of is that the force on a current carrying wire is equal to Bill sine theta, and we also need to be able to work out the direction of the magnetic force acting on a conductor by using the right hand slap rule. So let's have a look at an actual motor, a DC motor. So what we're going to do, we're going to draw firstly a pair of magnets. So there's one magnet, and here's our second magnet. And these magnets have a north and a south pole. As surprising as that may seem, but they do. So with an electric motor, with a DC motor, or any motor in fact, what we really, well, a DC motor I should say, we really want the magnetic field to be flowing in a fairly consistent manner. So we'd probably want this to be, for example, the north pole and of this magnet, and we'd want this to be the south pole of this magnet. So that's going to be south here, and this is going to be north there. And if we have that arrangement, then a fair chunk of the field is going to travel across that gap like this. Now, clearly we don't want these two magnets too far away from each other, otherwise a lot of this magnetic field is going to spill around and enter the rear end of its own magnet of itself. So we want these close enough together so a fair amount of the magnetic field passes from this magnet into this magnet. Okay, the second thing we need for a magnet is a conductor. Now, the simplest conductor that we could probably produce is a single coil. Now, I'll draw the coil over here first. So all the coil is a, actually I'll change my colour, I think. All the coil is a loop of wire, like that. This is a really simple coil. So that's looking at the coil from above. So what we're going to do, we're going to place this coil in our magnetic field, and we're going to put it in sideways. So in other words, we're going to put it in so that the coil, if we're looking at the coil from that direction, then we'd call that the A end of the coil, and we could call this the B end of the coil. So looking at it sideways, there's the A end there. So that's looking directly into that end of the coil. So we're looking into the coil there at A, and here's the B end of the coil over here. So if you can visualize, the coil is actually going into the page, going around and coming back out this way. So we're looking at the coil side on. So let's now add the final ingredient, which is current. So to make this motor work, we're going to need a current, and I'll just get rid of that. So what we're going to do, we're going to connect the conductor to a battery. So for our battery, I think we will go to green, and we'll say that this is the positive end and there's the negative end. So this is the positive end of the battery, and that's the negative end of the battery. And we're going to connect our battery to the loop. So we're going to connect it there at that end, and this end of the battery is going to be connected to that side of the loop. So if we look at our battery then, that means that the A side is going to be positive at the moment. So this is connected to the positive side of the battery, and our B side is connected to the negative side of the battery at the moment. So that's our battery. Okay, well, let's have a look what we've got here. If the battery is connected like this, with the positive terminal on this side and the negative terminal here, then positive current is going to travel around the loop in the clockwise direction. So the current's going to come out of the battery, travel around the wire like this, and back. So that will be the direction of our current. So if we now try to visualize this in this diagram, we can see that the current is traveling into the conductor at point A and coming back out of the conductor at point B. So we're going to use our cross and dot convention to represent that in this diagram. So the current is traveling into the conductor at that point and is traveling out of the conductor on that side. So what we can now do is work out, using our right hand slap rule. We're not going to worry about sizes of the forces yet, just the directions. We use our right hand slap rule. We can now determine which way these two conductors are going to want to go or move. And using our right hand slap rule on conductor on the A side of the conductor, we know the current's going into the page. We know the magnetic field is travelling from left to right. So that's our magnetic field there. And so using the right hand slap rule, we can see that our thumb would be pointing into the page. Our fingers are pointing to the right. So that means that the force on this conductor, on this side of the conductor, will be down. So the force acting on that side of the conductor is down. Over here, the current is travelling towards us. So our thumb's going to point towards us. Our fingers still need to point to the left. So if you arrange your hand, your right hand, so the thumb is pointing out of the page and the fingers are pointing to the right, I beg your pardon, not the left, to the right, your palm of your hand is facing up. So the force on that side of the conductor is upwards. So because these two conductors are connected, you can see that this is actually going to produce a rotating effect. So if this was so I'll draw the rest of the conductor there. So if you imagine this was connected to some sort of a wound around a piece of timber which could spin on an axle or something, you could see that this conductor, this side of the conductor would want to move in that direction, and this side would want to move in that direction. So we're starting to get some rotational motion. And at the moment, the conductor is going to want to move in the anti-clockwise direction. Okay, so we can now see where these forces are coming from and how we're starting to see how we're going to get a rotational motion in our motor. In video 3, we're going to look at this in more detail.